Hi, everyone, and thank you for attending today's webinar, Why Collaboration is the Crucial Factor in Designing the Most Efficient PV Farm Layout. I'm Kelly Pickerel, editor with Solar Power World. And before we get started, I wanted to let you know that slides are available to view at any time in the resource window on your screen. This webinar will be sent to all registrants, so you can view it again at a later date. Please submit any questions related to today's webinar in the Q&A window. We'll try to answer these during the webcast, but if we do not get to your question, our presenters may reach out to you afterwards. Finally, if you're watching this webinar on demand, you can still use all of these features. So let's get started with today's webinar, Why Collaboration is a Crucial Factor in Designing the Most Efficient PV Farm Layout. Today's speaker is Maxim Markovich, who is Chief Technology Officer and co-founder of Creo Software. Today, we'll learn more about designing the best solar project through collaboration and software. So now I will turn things over to Maxim.
Thank you, Kelly. So hi, everyone. Thank you for having me here, Kelly. So it's a pleasure for me to speak about collaboration and collaboration, especially why the collaboration is a crucial factor in designing the most efficient PV farm layout. So just a quick introduction. So I came from industry. So I was working as a structural engineer, CAD manager, BIM manager, and finally we organized a team and we started to build a software products for the IEC industry. And basically one of our products is PV Farm Configurator. And during this webinar, you will see some of the outputs and outcomes of the software. So I'll just go straight to the next slide. And here is our quick agenda. So we're going to talk about what's PV Farm Layout in general, how the team grows with the project capacity, design and pre-construction teams. Also, we're going to talk about team size and communication complexity. We'll dive deeper into process flow for a very, let's say, typical utility scale PV farm project. Also, we will talk in general about what's the feedback loop, and we'll go through a couple of examples of external feedback loops and internal feedback loops. And finally, we kind of got all the things together and answer on the question, why is that collaboration is a crucial factor of designing the most efficient PV farm layout. So let's get started and let's go to the next slide. And first of all, again, what's PV farm layout, right? So the solar PV farm layout is a racking or mounting plan of PV modules, which shows the information about the site, about point of interconnection and design system characteristics, right? So PV farm layout is the most important document that reflects chosen single line diagram and equipment specification. And also it serves as a basis for energy performance analysis, cost estimation, construction schedules, and also obviously construction drawings. This is approximately what you see on the slide. This is how it looks like. So you can think about solar farm layouts as a floor plans for single family houses, but I show the audience either way of what does it mean. So solar farms, as they are layouts, they can be of different sizes, from a couple of megawatts to thousands of megawatts, from a couple of acres to thousands of acres. So now let's just jump real quickly and talk about what kind of team working with solar PV farm layout, and also like how the team grows with the project capacity. So obviously collaboration is about people, so this is why we need to talk about it. And if we go to the next slide, you will see a very simple dummy chart is about how the people involved in pre-construction and design depend, how the number of people depend on the project capacity. So basically, a small one megawatt project can be fully designed by a couple of people, while the one around 100 megawatts will require dozens of people. So I would say, again, it doesn't depend linearly on each other, but it's fair to say that the more significant project we have, the more people we will need to be involved in design and pre-construction. And just a couple of notes about the chart itself. As you see, it's kind of snowballing in this specific area. I would say from 12 megawatts up to 50 megawatts, and then it's fairly flattened. And so basically the amount of people which will be involved in designing, let's say, 330 megawatts and 470 megawatts will be approximately the same. Again, in accordance with our research, it will be around 50 people. Again, it's just design and pre-construction. So, and obviously the project complexity is not really super related to the project size, although taking into account the fact that solar PV farm layouts, they're very repeatable. So let's say there are a lot of parts that actually being repeated across the layout. This is why even smaller project can be less complex or less complicated. Let's say the left one with 330 megawatt DC can be slightly complicated than the bigger one with 470 megawatt DC because of some geology conditions, because some sophisticated boundaries and other things. But basically, the size of the team that will work on this will be fairly constant for both of those projects. So yeah, so we talked a bit about what does PV farm layout means, and also we talked about the team size and the people involved in the producing PV farm layouts. Let's just go to the next slide and talk a little bit about how the team size and communication depends on each other. And obviously, the bigger team we have, the bigger communication complexity. I would say, if we'll go to the next slide, just real quickly, I would say that the communication complexity grows quadratically with the team size. You probably heard about Metcalfe's law. That's about telecommunication network. And basically, when you have, let's say, 2 members, you have 1 line. When you have 3 members, 3 lines. When you have 5 members, you have 10 lines. So how people can communicate to each other, right? And so when you have 10 members, you have 45 lines. Again, in the real life, it's a little bit different based on hierarchy in the company and all the stuff. But the main point here, the main takeaway is that the bigger team you have, the more complicated communication will be and collaboration of that team. So as I said, communication complexity grows quadratically with the team size, but the consequences of the broken communication, I would say they grow exponentially. So in designing PV farm layouts, as well as developing software products, broken communication, I would say, is one of the biggest threats to the project. So yeah, so we discussed a bit the team size, the communication complexity, and how it grows with the team size and the project capacity. And now let's talk a bit about the process flow itself. For the sake of this webinar, we will consider a pretty typical utility scale project. I would say it will be around a couple of hundred megawatts. Okay, it's not typical one. It's quite a big one, and we're going to consider how this project is being designed and the key roles involved in this project before we will jump and talk more precisely about trade-offs, about feedback loops, and other things. So, so let's, again, just to summarize, if we go to the next slide, right? So back to PV farm layouts. So design and pre-construction. We have many people involved in the design and pre-construction. If we're talking about, let's say, 100 megawatts utility scale PV farm, right? The job of those people usually is broken down into areas of expertise or disciplines. So obviously, when you produce a layout, those many different areas of expertise, they are overlapped. So the most important ones you can see on the slide, this is energy modeling, electrical engineering, procurement engineering, cost estimation, construction, civil engineering, and many more. So these are roles and these are disciplines. They're, let's say, from the firm called EPC contractor, right? So, and typically we're going to talk about the process when owner or developer meets EPC contractor, and we're going to talk about how they communicate externally and internally. So just a couple of explanations about this scheme, right? So let's say we have owner or developer. So we have someone who want to build a solar farm. Typically people, they want to build a solar farm because they want to get a profit, or maybe they're big fans of renewable energy, but in most cases they still want to get a profit. And so what they do during feasibility stage, they do a lot of assumptions and they build a lot of guessings about what can be built on a particular parcel of land. So if I will simplify, they basically calculate the residual land value, what you see here, right? So they try to understand what energy value they can get out of specific parcel of land, and then they just minus all the spendings they need to pay in order to build this. Again, there are obviously many things that they need to pay for, let's say, for the planning permissions, for bankable feasibility study, for EPC contract itself, for any other things. So there are many more. But if we will simplify, if we will basically calculate how much money we will earn with this gross energy value, let's say for the design, for the life cycle of the project, and then we will we will minus all our costs we will actually pay for building this, we will get what's left on the land. And so if this what's left will be sound good around our benchmarking and around our expectations, then that's fine. That's a financially viable project and we can go further. So basically, let's say this is the place where external owner or developer meets EPC contractor. Typically, again, the owner have a parcel of land in mind. They already started to gather some information about site. So they did some feasibility study, maybe found some funding or loan to build a PV farm, right? And again, this layout they create is a very conceptual one. And then they kind of, owners or developers, they gather all this information and produce what's called request for proposal. And this request for proposal is an input for EPC contractors or any other contractors that participate in a tender. So basically, the communication begins somewhere here when there is an RFP is being sent to EPC contractor. And typically there is someone from an EPC contractor side who is actually responsible for communication on the EPC side. In my case here, it's a kind of energy modeling guy or energy performance, senior energy performance modeling engineer or manager or whoever, someone responsible for that. And basically the very classical conversation, it looks like, okay, look, we have this parcel of land and we want to build this amount of capacity PV farm. What can we do? And so this is the first feedback loop. And then basically, this is what's happening in between owner, developer, and EPC contractor. And there are many other internal feedback loops which are happening inside the EPC contractor between those guys. So we're going to talk about that in details a little bit later. So, but before, so basically, again, just to the root of the topic, those are feedback loops in between those people, like feedback loop between energy modeling, electrical engineering, civil engineering, cost estimation, construction, civil engineering, procurement. You can think about, let's say, again, let's say energy modeling, they need to achieve 180 megawatts of power. Then the civil engineers, they say it's impossible. So if it's physically impossible to place the trackers equal to 180 megawatt of power, then that's it. But in the most cases, it is physically possible, but it's just a matter of how much money you're going to spend on doing civil grading or doing electrical engineering, for example. So yeah, we'll talk about it very soon. But before, let's just discuss a bit what are those feedback loops mean and what does it mean, feedback loop. So as you saw from the previous slide is more like a back and forth between people. And this is a very this is a super simplified scheme of what it is, right? So basically, I think this scheme is applicable not only for PV farms, but also for any building design. So basically we have three main activities: plan, design, analyze, right? So typically we plan goal or we plan what if. So then we design scenario or design a couple of scenarios. And then we analyze trade-offs in between those scenarios. Then we got some new information, new insights, and we go for the second loop. So this is basically the very simple mental model that helps me kind of to build the value chain and the connections in between different clients and different project shareholders. So again, just to summarize, feedback loop is a process in which the outputs of a system are circled back to adjust the input until all process participants find an agreement. So in that case, the solar design feedback loop refers to analyzing PV farm layout metrics to create a better layout. So you basically analyze layout to create a better layout, to come up with new ideas or with new requests or with new goals. So let's go further. And we're going to talk first of all about the external loop, which happen in between EPC contractor and developer. And this is probably the easiest one. Let's jump to the next slide. So yeah, just one very specific example. Let's say we have developer, and the request can be, can we get a 570,000 megawatt hour as a first year energy by using this type of modules, let's say Longi 550, and by using 76 sun-grow inverters with a specific megawatt DC power on the side below. So this is a very simplified version of request for proposal. So we have site, we have some restrictions, we have, I don't know, all the survey, we have some flooding zones, we have many different sources of information. And the point is to answer, like, can we get this capacity or can we get this energy? And obviously, or can we stick to this specific owner specification? So there are different types of requests, but this is a simple one. And then let's say, so this is that was the goal, which was created by developer, right? Again, if you go back here, so that was the plan. They created a goal, and then with this goal, it comes to someone who can actually build a scenario or design a scenario. And let's say that then the communication go further. So yes, we can. So here's what we got. Here's what we got. This is our layout. It has this capacity, this energy. Revenue over 25 years will be around 530 millions. And EPC contract cost will be around 180 millions. So again, all those numbers, they're fake, but still keep them here in order to have more realistic examples. So we got this scenario, and then the first question from developer might be, okay, the cost for the EPC contract is too high. So it increases our cost per watt DC we put as a main assumption in our financial model when we took a funding, right? And so in that case, that might create problems for overall viability of this project. But then EPC contractor replies, but to achieve your spec requirements, we needed to go tight. We shifted trackers here in order to get more DC because we couldn't get UDC immediately. We shifted trackers there. Also, we used 1, 2, and 3 strings trackers. Every string is around 29 modules. And also we were quite aggressive with the pitch of 20 feet and to height preference because we needed to actually stick to those requirements. And then the next question can be, okay, is there any way to reduce the construction cost? So this is the example of a very initial like feedback loop. So there was a goal with a specific equipment, right, with a specific target. Then there was a request to design a specific scenario, and then during analyzing this scenario, it seems like, okay, it's too expensive. So it's too expensive. This is an acceptable trade-off for us. We cannot pay so much money. So, and then it leads us to actually changing our goal, or maybe thinking about what we can do. So that's kind of initial feedback loop, which will basically lead to the next kind of iteration of feedback loops. So, okay, what if we increase the row space trying to keep the same first year energy output but reducing the capacity? What if we use only 116 mods trackers, which is 4 strings trackers with 2 height preference, keeping a bigger row-to-row space? Or what if we will use these, 4 strings trackers and apply bigger lead assembly or trunk bus electrical pattern in order to reduce the electrical cost? So you see, basically the first feedback loop iteration, it just leads us to creating more and more different goals and what-ifs. And obviously, the initial circle or the initial loop, it usually happens with a very rough estimation, because, quite often contractors, they just come up with a price in order to see if the developer will be happy to proceed with this price, so then they can readjust certain things. But it's anyway back and forth, circles and loops. So then we have those scenarios I mentioned, and obviously each scenario needs to be considered, and each scenario needs to be created and designed. And let's say we designed 3 of those scenarios. As you see, when we increase the row-to-row space, let's say we got less capacity, right? So our target was, our target was 327. So we got 272, which is less capacity. But at the same time, we got more energy, which is happened because you created more space in between trackers. So they stopped creating shading for each other. So we started to lose less energy. And it turned out that initial specs requirements, they were not super smart, because it was a clear overuse of equipment, and it just didn't make sense to create such a specific layout. But it's just something which can be understood only after certain iterations or only after certain conversations. So then this is our revenue and this is our cost. So cost went down, which is cool, but we continue working on the next what if. Next what if, okay, we're gonna use 4 string trackers, and basically only 4 string trackers, and with the same row-to-row space. In that case, again, we're losing more capacity, because you cannot fit, let's say, if you have 1 string, 2 strings, 3 string, and 4 strings trackers, so you have a lot of stripes. You can fit more of them in the layout in any side boundaries. When you have bigger trackers, you cannot fit as much power as you did with a variety of trackers. So you lose capacity, but at the same time, you lose also energy, and you also reduce your revenue. But at some case, this specific scenario, from a profit standpoint, can be more preferable. For example, if you will have a look, we lost, like around 50 millions for 25 years. But at the same time, our cost here went down by 20 millions, which is also can be like the cost for construction you will pay in the coming years, and the revenue you will receive in the 25 years. This is where the sophisticated financial model calculations come in a role, because developers, they need to take those things into account. Loan percentages, rates, and all this stuff. And then again, the third case, when we use different electrical pattern, which actually, by the way, can also, we can stick to the same energy if we will stick to the same DC losses or to the same voltage drop. But cost again might be even cheaper, So basically, what I'm trying to show here is that the communication which is going in between the developer and EPC contractor is just going through our feedback loop. And every time, every new every new iteration, just readjust the goals, readjust what-if scenarios, then it creates new options. Those options are being analyzed, and there are certain trade-offs which are being considered and that are being that are being pre-calculated, and that's how it works. So this is kind of external feedback loop, but we also can dive deeper and talk about what's going on inside EPC contractor, what type of feedback loops are happening there. So it's a little bit more interesting because we have many more roles. So again, when we're talking about external feedback loop, that's only developer, owner, and EPC contractor. When we're talking about EPC contractor, that's all about, you know, electrical. For example, performance modeling engineers, they're responsible for, in general, like performance of the PV farm, energy modeling, losses, and all this stuff. Electrical engineers, they're responsible for the wiring, low voltage wiring, medium voltage wiring, and single line diagrams and all these things. So then civil engineers, they're responsible for grading, for hydrology grading, for basins, for any other things on the layout. And procurement engineers, they're responsible for buying, you know, wiring and ordering specific equipment. And there might be also interesting fights between electrical engineers and procurement engineers. I'm calling them fights, but in a healthy world, that's just a healthy conversations, because the most optimal electrical wiring system might be hard to buy in the market. So then it doesn't make any sense. So this is why it's kind of, again, feedback loop between those guys. And the same happening between civil engineer and performance modeling engineer. So sometimes you cannot feed the needed capacity in the site, or you can feed, but it will be very expensive, and that's always a trade-off. So estimators and obviously pre-construction managers. And so let's just consider a couple of, I would say, quite common cases about what kind of feedback loops there are internally inside EPC contractors. Again, this is something what I mentioned before. Let's say, what if we design only perfectly balanced blocks? How much capacity will we lose in the comparison with the maximum power mode? When I say maximum power mode, I mean, is that like you basically need to fill the whole site and you need to extract as much power as possible. But obviously when you're doing this, and when you're limited with a specific equipment, let's say you don't have a choice. You should use one type of inverter, SunGrow 3600. And basically, when you want just fulfill your site as much as possible, you will end up with different blocks. So with different DC power that comes into inverters. And obviously, when you have this different DC power, let's say for SunGrow 3600s, by applying DC-AC ratio 1.2, 1.3, the ideal DC power which we want to come into inverter would be around 4,300s, maybe 4,400s, right? But if you have unbalanced blocks, you will clip power. So let's say if there is a 5,000s come to your inverter, so it will clip the power. And at the same time, when it's, I don't know, 2,000 kilowatts DC came in your inverter, is just not efficiently used inverter, right? So basically, and in a best balanced blocks like here, we can see that all of the blocks, they have the perfect DC power comes into inverter. These are central inverters. And obviously, but at the same time, we have more space which is not used basically. So we can see this space here, space here. So it's basically we got less DC power. And if you will check capacity, we have 295 versus 279. So the balanced blocks gave us less power and less energy at the end of the day. But at the same time, we also reduced the number of inverters, 64 versus 73. and let's say our average DCIC range is fine. But again, if you will check this specific place, you will see that there are many, let's call, bad blocks. And so that fact that average DCIC ratio for the whole site is a healthy one, it doesn't mean that that's a cool site, right? So you might still have a lot of problems. And obviously you can see revenue comparison and you can see cost comparison. And cost comparison obviously happening because you have pretty ideal blocks. When we do this kind of optimization with the best balance, we try to create a very compact block. So we try to create efficient combiner box circuits, which means that you will spend less money on low voltage wiring, which means that you will spend less money on building the project when you have accurate and nice blocks and, you know, this type of stuff. So basically you see that the best balance option, it can be from a construction cost the best one in that case, but obviously it will work only in the case if those numbers about capacity and energy, they will work out in the spreadsheet or financial model from the developer. So again, the same story, the same feedback loop, internal then external. So if we go further, we'll consider another case. This one is also very popular, and basically, you know, the typical requirement from request for proposal from owner or developer is that, you know, we want to achieve, you know, 1% DC loss average, you know, and let's say maximum loss should be 1.7%, or maybe like maximum loss should be 1.7%. So we shouldn't go above this one, but the average loss shouldn't be higher than 1.2. And so basically this will lead us to, you know, what if we compare the cost savings of ensuring an average 1% DC loss to 1.5% DC loss? And so we created one layout and we used one type of wiring, and then we created another one with the same temperature. Let's say here we have conductor temperature 75. We used harness, so we used harness. I think it was like 2 harness per tracker, and so we got different wiring based on the requirement, and so we achieved 1% DC loss and 1.5% DC loss. And as you see here, the capacity is the same, and but energy obviously a little bit different. So you have bigger losses here, and this is why you have less energy. Revenue also different, so less energy, less revenue. Obviously, it's also connected to developers' spreadsheet, to PPA agreement, whether you have battery storage or not. There are many factors, but in general, you can always build up some assumptions and think about how to compare those options. So, and then we have cost. And a fun story about those scenarios is that we lost 2.3 million in revenue over 25 years, but we saved like 4.8 million of cost for the construction, which you will basically pay somehow the first years of the construction, and, you know, paying for 4.8 million in order to get 2.5 extra in the next 25 years doesn't seem like a right business decision. So yeah, that's a typical good one trade-off. So then let's consider another one, which is also very common. So we met different EPC contractors, and the role of the person responsible for producing layout is also different. In most cases, they are civil engineers. Sometimes they are electrical engineers. So basically, it also varies from project to project. But let's say we have a layout, and we achieved our targets. So we're fine with the capacity and we're fine with the energy. And we have a very dummy question from someone. it can be a pre-con manager or whoever, right? What if we will move array A, so which is this one, to place B, so somewhere here. So basically, we have excessive land, which is also a very rare case, but let's say we build this in a way, and we're just wondering like what will happen if we will move this block here, because it seems like we have enough place here, and our substation is somewhere here, and yeah, and so we consider option A and we consider option B, and basically you can see that indeed when we moved block from the place A to place B, basically civil costs become more expensive. So basically we pay 3 million more for the civil cost, because probably initially this layout was made by civil engineer, and civil engineer saw here a very steep slope or something like that, and they just make a decision, no, we're not going to build here because, you know, it doesn't make sense, so we're going to build here. But then, because taking into account the fact that our substation is somewhere there in the top right corner, and also here is a, I think it's, oh, yeah, so overhead line, and basically it looks like electrical cost much cheaper for the option B, which leads to the fact that in total, option B is more preferable. Although when you see from a one Ambilson point, you can think, okay, actually, too much grading, too much dirt to move. Let's move this block there. And then when you have a proper communication and proper feedback loop, so you see here goal, then we have what if, goal or what if, then scenario and trade-off. It all leads us to the same feedback loop here, right? So we have goal, we had goal, we build up some scenarios, we analyze trade-off, we come up with a new plan, or we got something. Okay, finally we good. So that's nice. Let's move on. So that was the basically the third feedback loop example, internal one, and there are obviously many more. They're related always in civil versus electrical, electrical versus energy, energy versus civil versus procurement, logistics, and many, many other things. So, and obviously, so we considered a couple of options of different internal feedback loops and external feedback loops, and now let's try to answer to basically the main question. So why is that collaboration is the crucial factor in designing the most efficient PV farm layout? And so I would say before doing that, let's clarify something. So first of all, collaboration involves working with someone to produce something, right? And the second one is that collaboration presupposes communication and synchronization. So these all things are included in the collaboration, right? So basically, if we will take our feedback loop, the one we were working on and we were working with, so if we will take this one and cut it in a straight line into two parts, from the left side, something that we can do only collaboratively, and from the right side, something that we can do by solo effort. So then you will see the picture which you see right now in front of you. So basically, the point here that we can only do activities like planning goals and analyzing trade-offs by working collaboratively. And this part of the feedback loop is the most significant one. The activities from the left, these ones, they can be done, you know, like not necessarily collaboratively, and but also so they can be done by solo effort. But the problem is that sometimes it also done collaboratively, especially when design of the specific scenario involves a different specialist, different areas of expertise. Then we cannot do it also by Solar, so we will still need to do it collaboratively. So basically, we have even if we don't consider design as a collaboration, which is strange, right? We have a bigger chunks of activities. So we have plan activity, analyze activity, and outputs. We have trade-offs, and we have goal, which are done only with the help of collaboration, and then the fewer part, which is done without collaboration. And that means the collaborative work is it's even bigger piece that we see in the picture. So basically, to add a bit more weight in the addition to the feedback loop mental model, let's call it feedback loop mental model, I would mention that we as a company have been involved in hundreds of conversations about feasibility studies around residential and mixed-use buildings, and also around PV farm projects, PV farm layouts. And also we've been shadowing design and pre-construction meetings at different phases of the PV farm layout projects. And we would be safely to say that actually 80% of the time, 80, so not 2/3 or 1/3, I would say 80% of the time people spend on collaboration, synchronization, and communication, right? And only 20% of the time they spend on making solo efforts. So when you actually sit and design something. So obviously it may vary from the project to project or from phase to phase, but we are pretty confident about this assumption. So basically the first reason, let's go further. So basically the first reason why collaboration is the crucial factor in designing the most efficient PV farm layout is connected with the fact that in a typical design process with multiple projects shareholders involved, it simply has a more enormous mass in comparison to solo effort. So it's just bigger mass. So it's so simple, right? So the second reason is related to the main goal of the feedback loop. So the main goal of the feedback loop is actually analyzing PV farm layouts to find the most efficient one. So we are seeking for the most efficient layout. And collaboration is like a chain of the whole feedback loop mechanism, right? And a broken chain prevents us from sought for the most efficient PV farm layout. And by the way, we can find an exact definition of what does the most efficient one mean only through collaboration. Otherwise, as I showed before, civil engineers will think about minimizing grading, while electrical engineers will push for, I don't know, the cheapest or the most efficient wiring. So I bet we'll get different layouts. So the point, again, just to summarize, so the first reason is just in the feedback loop, which is typically happening between project stakeholders and project shareholders, there is just a bigger chunk of collaboration rather than solo work, which is quite obvious, right? And the second one, you can define what does the most efficient layout mean only through collaboration, because you have different points of view and different perspectives on the same problem, and only through collaboration you can figure out what does it mean for you. Is it the cheapest one? Is it the best energy? Is it the least maintenance cost? Is it what does it mean, the most efficient PV farm layout, right? So when the collaboration is a key to this answer. So just to summarize, so okay, collaboration is essential, so what? And here is just a very simple conclusion. Obviously, if we are or you are industry players, developers, contractors, manufacturers, I think like we should invest in collaboration and spend time improving it, because sometimes people they run for technology, but no technology can save the team if they don't work together. So basically, collaboration is the key. And also for people like we use this inside of those small insights when we build software products, because we build them with collaboration in mind. Because it's it's the basis, it's the basement of everything which is going in the design pre-construction process. So yeah, that's yeah. Thank you, guys. That's my short presentation. Yeah.
Right. Thank you, Maxim. Hopefully now I don't sound like I am underwater anymore. Now we are in the Q&A portion of the webinar. So if you have any questions, please submit them in the Q&A portion on your screen. So our first question, is collaboration equally crucial for small, medium, and large solar farm projects?
Mm-hmm. Yeah, good question. Yeah, as we mentioned during the presentation, obviously the more people involved in the project, the bigger importance of the collaboration. But in general, if we even start from 2 or 3 people, 3 folks involved in the project, it's already pretty crucial. So yeah, I would say that the bigger project, the more important collaboration. I would say when the bigger project, the more harmful broken collaboration. And so the smaller project, the less harmful collaboration problem. So basically, but it's important for each scale, for each project size. Yeah.
Okay, perfect. Next question is, how can advanced automation improve collaboration?
Okay, good question. So basically, again, as you see, the collaboration is happening especially across different areas of expertise. So we have, in my examples I explained in the presentation, we have, let's say, civil engineers, electrical engineers, and energy performance modeling engineers. And obviously, if the technology, if we can incorporate with the technology different areas of expertise in one software, so it definitely will be happening in a more efficient way. So people will find the answers on their what-ifs much faster. And so the overall process will be a smooth one. So basically, yeah, so the advanced automation can help us to kind of to have a computational power in order to consider different angles and different areas of expertise simultaneously. That's the answer, yeah.
Okay. This next person is wondering if there is a free trial of the Creo software.
Yeah, sure. This is one of our software products, which is, you can find at pvfarm.io. So, and yeah, we have free trial, and we also help to use our software. We help with site boundaries, we help with projects. So feel free to reach out to us. We'll figure it out. Yeah.
Okay, someone is wondering where you get your insights. Like, how did you explore problem space when building the PV farm configurator?
Yeah, it's a good question. So obviously, you cannot read a book about how to design PV farms, especially it's fairly new industry, and the knowledge in there is changing very quickly. And obviously, the answer is the market. We have people, we work together, we help them solve their problems, they help us understanding problems, and basically working with partners, working with contractors from industry, we get in knowledge, and then we incorporate this knowledge into software we build. Yep.
Mm-hmm. Okay. Do you have any experience with agrivoltaic projects?
Yeah, I like this question. So we don't have. So we have some requests about it, but we do not have any experience at the moment.
Okay. As a reminder, you can continue to submit questions in the Q&A section on your website. This next question, how did insights you shared about collaboration help you shape the PV Farm Configurator software project? Is there any specific technology built for this?
Yeah, sure. Yeah. I like this question. So obviously, when we started to build this kind of configurator, we knew that people will need to work in there together. So basically, we started from the very beginning, building the environment where people can launch computations in a multi-threading, so they basically can work in a parallel. So like couple of folks can work simultaneously in one project, they're doing different changes, and we also incorporated the versioning, like a Git versioning in the software. So basically, if like three persons simultaneously work on one version, and then everyone did some changes, and they will save their changes, they will kind of they will save different branches with the basis from the version that we're working on. So yeah, basically, I think it's when you have collaboration in mind, and when you have plans about incorporating collaboration, it drastically changes the way how you build software. So yeah, it's important.
Okay. I think this will probably be our last question. It is, what advice do you have for smaller companies that would like to begin landing bigger projects?
Smaller companies. Yeah. Are we talking about developers or contractors?
Yeah.
So it's because I think it's really different. So let's say if we're talking about developers, I think it's just step by step. You just as you know, you just become more advanced. You grow your skills as in any specific activity you do as a person, and then you just constantly upgrade, and yeah, I feel like it's happening like that. If we're talking about contractors, especially if we're talking about EPC contractors, I think it's actually the same story, but it's a good question. I need to think about it. So I like it.
All right. Yeah, you could get back to them on that one. Well, that is all the time that we have for questions today. If you have additional unanswered questions, please feel free to reach out to Maxim on your own. This webinar will be shared with all registrants, so you can view it again at your convenience. So I would like to thank Maxim for being here and Creo for sponsoring today's webinar. And thank you to everyone for joining us today. I hope to see you at more Solar Power World webinars in the future. Thank you.
Thank you very much. Bye.